Okay, this lecture is going to be over section 8.4. So TLDs, or thermoluminescent dosimeters, are going to be used for in vivo dose verification, skin dose, phantom measurements, personnel radiation monitoring, that kind of thing. Ring badges are frequently worn by radiation workers who handle radioactive sources, particularly, the brachytherapy. They will monitor the dose close to the worker's hands, and a wide variety of materials exhibit thermoluminescence. For dosimetry purposes, TLD materials are crystals with impurities that are sensitive to radiation. When TLDs are irradiated, a small fraction of the absorbed dose is stored within the crystal lattice. When you then take the TLDs and heat them, some of the stored energy is released in the form of light. Furthermore, the amount of light energy released increases with an increasing absorbed dose in the material, and this explains the name thermoluminescence. Thermo meaning heat, luminesce, light. There you go. TLDs can be reused after reading, but it is necessary to anneal them by subjecting them to special heat treatment to bake out any residual signal and to condition their sensitivity. TLD materials come in a variety of physical forms: chips, rods, powders, etc. TLD micro rods are common. Figure 819. These guys. And these rods, these are rods. These are rods have dimensions. That sentence is not written very well. The rods have dimensions of 1 by 1 millimeter thick and 5 to 6 milliliters long. Cost about $1 to $2 per rod. Most frequently used TLD material in radiation dosimetry is lithium fluoride. The effective Z is 8.2, which is similar to tissue and air. So the efficiency of TLD material can be defined as the TLD light energy per mass divided by the absorbed dose. The efficiency for lithium fluoride is pretty low, so it's very tiny. They're heated during the read process. As the temperature of the TLD increases, the brightness of the thermoluminescence increases until it reaches some maximum value at a temperature called Tmax. And then the brightness begins to decline. So you can see here the TLD glow shows the brightness of the sample as a function of temperature. So the maximum occurs at a temperature Tmax. Many TLD materials have material glow peak curves. The details of the glow peak and the value of Tmax depends on the heating rate. So a TLD reader heats the TLD and measures the light emitted. A photomultiplier tube detects the light and converts it into an electrical signal. And the PMT has a high voltage across it, typically within 750 to 900 volts. The circuitry inside the reader must sum the total light output. The result of the reading is displayed in terms of the total charge output from the PMT in units of either micro coulombs or nanocoulombs. The highest temperature that the TLD reads is generally around 300 centigrade. TLD reading is directly proportional to the dose for relatively low doses. The TLD material is said to be linear at low doses, meaning that twice the dose will result in twice the reading. Lithium fluoride TLD material is linear up to a dose of about 300 to 400 centigrade. So this is the picture of the TLD reader. You got the sample placed in the drawer on the tray, which can be heated. The tray is sometimes called a planchet. The drawer is closed and the TLD is heated. The light from the thermoluminescence passes through an optical filter here and into the photomultiplier tube. The optical filter absorbs infrared light emitted by the heat planchet and prevents it from reaching the PMT. A PMT converts the light into electrical current, and the charge produced by the PMT is summed and then displayed on the front panel of the reader. So TLDs must be calibrated by exposing them to a known dose and then measuring the response. And that's in units of centigrade per microcoulomb or centigrade per nanocoulomb. The usual procedure for in vivo dose measurement is to take several TLDs called standards and expose them to a known dose that is close to the dose one expects to measure. This procedure provides a calibration factor. Several more TLDs called unknowns are then used by attaching them to the patient during the treatment. The standards and the unknowns should be drawn from the same group or manufacturer's lot. The sensitivity may vary from lot to lot. The TLDs are then read, and the calibration factor from the standards is used to estimate the dose received by the patient. The unknowns are simply placed on the skin if it is desired to determine the skin or entrance dose. If the dose at DM is desired, then the TLDs will be placed on the patient's skin and covered by a tissue equivalent material of the necessary thickness. And that's referred to as bolus. An example of the measurement process is here in example 8.2. So a patient's skin dose is to be measured using TLDs. So you got 6 TLDs removed from a packet. 3 of these are used as standards and are exposed to a known dose of 100 centigrade. 3 unknowns are placed on the patient's skin. The average reading of the standards is 64.8 nanocoulombs, and the average reading of the unknowns is 83.2 nanocoulombs. What skin dose did the patient receive? So the calibration factor of the TLDs is this divided by that, since that is known. So you get 1.54 centigrade per nanocoulomb. The patient's dose is then, you've got the number of nanocoulombs here, you multiply it by the calibration factor, and you come up with 128 centigrade. They're small, they're reusable, and they have a wide dose range, and those are the advantages. And they are near tissue equivalent. They do not need attached wires like diodes or MOSFETs. The disadvantages are that the reading is not instantaneous. They have to be exposed and taken to the reader. Another disadvantage is the possible loss of a reading. They can only be read once, and thus there is no permanent record because it cannot be read again later. For in vivo, the use of TLDs is declining in favor of diodes, MOSFETs, and OSLDs, if your clinic has them. So, OSLDs are optically stimulated luminous detectors, or luminescence detectors. And this utilizes the release of energy stored in an insulator or semiconductor as a result of exposure to ionizing radiation. The energy is released in the form of light. Energy release is stimulated by exposure of the material to light. The optically stimulated light emitted is proportional to the absorbed dose. OSLDs are similar to TLDs, except that the stimulation used to release the stored energy, the stored light energy, is light itself rather than heat. These dosimeters are small integrating dosimeters, as are TLDs. The OSLDs are packaged to prevent them from ambient light. They measure the cumulative dose they are exposed to. Some of the absorbed energy from a radiation is stored in the crystal lattice, just like for TLDs. The only material commercially available is aluminum oxide, the small amount of carbon introduced into the crystal lattice, or carbon doped. The applications of these dosimeters are the same as for TLDs, in vivo dosimetry and personal radiation monitoring. These dosimeters are used by a large commercial firm or Landauer in their personnel radiation badges. Aluminum oxide has an effective value of 11.3 in comparison to 8.2 for lithium fluoride. So this material will over-respond in comparison to water, have photon energies below 100 keV. So you can kind of see it here. There's an OSLD in its carrier, and the carrier is open to view the OSLD. So normally it's kept closed to avoid the light exposure. So if you've got a reader here, the sample is stimulated with light. The OSLD in turn emits light in a different wavelength that is detected by a photomultiplier tube. The amount of light detected is proportional to the dose absorbed by the OSLD. So this verbally describes a lot of the things that we just went through. So it only the process here is that a light is used to provide stimulation and can be a laser or LED. Green LED light is commonly used. The detector is a photomultiplier tube. A filter is placed in front of the PMV to block the stimulus light, which is orders of magnitude more intense than what's going to be luminesced. Commercial readers use a short stimulus period of about a second. This only depletes a small fraction of the stored energy, and therefore the OSLD can be reread with a negligible loss of signal, unlike TLDs, which can only be read once. And now, film. The degree to which film is darkened by radiation exposure is related to the dose received by the film. Traditional radiographic film consists of an emulsion 10 to 25 micrometers thick of microscopic grains of silver bromide, coated on either one or both sides of a plastic film base. When radiation strikes the grains, they become susceptible to chemical change. They form a so-called latent image. The development process leaves small grains of metallic silver. The silver in the unexposed areas is washed away, and the portion exposed to radiation appears dark. A negative image of the radiation field is the result. A measure of film darkening is provided by the degree to which light is attenuated in passing through the developed film. A measure of light attenuation by film is called its optical density. The optical density is defined in terms of the light intensity incident on the film and the intensity of the transmitted light. The percentage of transmitted light is I sub t over I sub o times 100%. Notice that I sub t is in the numerator. As an example, if 10% of the light is transmitted, then IO divided by I t is going to be 10. And then if you flip that around, and OD is going to be equal to 1.0. So let's take an example. What percentage of incident light is transmitted through a film that has an optical density of 2.5? So the optical density is equal to 2.5. That's equal to the log of the incident over the transmitted intensities. If you exponentiate both sides, you come up with this. If you take this result here, and you take the reciprocal of it, and then multiply it by 100, you end up with this. So the percentage of transmitted light is going to end up being this, which ends up being 0.32%. And here you can see the light in incident light on the film, and then you can see what's transmitted. And this statement is true. Silver halide film is no longer used in most radiology or radiation oncology departments. We've just gone past that. But radiochromic film is still widely used. So a manual densiometer for measuring the optical density of a film. You place it on the platform, and the arm is pressed down. Light emerging through the aperture passes through the film, and then the OD is read from the digital display. So that's kind of neat. You can use equation 8.7, the optical density equation. And it's given an example 8.3, which we just went through. The usable range extends up to about 2.0, which corresponds to about 1% light transmission. Above this, the film is very black and little useful information can be obtained. Optical densities are additive. The optical density of two films superimposed is the sum of the individual optical densities. And then we just went over the densiometer up there at the top. Generally, in most cases, you're not going to end up using a lot of film. Although I will say, in the clinic I currently work, we do have a film program, in which case this is used for in vivo dose computations. Even film that has not been exposed to light will, when developed, attenuate some light because of the plastic film base and because some silver grains are developed even in the absence of radiation exposure. The former is called base, and the latter is called fog. So the former here, the plastic film base, that will attenuate some light, and because these grains are developed even in the absence of radiation exposure, it's called fog. So basically, you've got a couple of problems here that you have to account for. So base plus fog optical density is about 0.2. So the net optical density is defined as the total optical density minus the optical density of base plus fog. It's right here. Here you can see the relationship between net optical density and dose for a Kodak XV film exposed through 10 MV rays. So for low doses, the relationship is linear. A blue line has been drawn through that to illustrate that. For higher doses, the relationship between becomes nonlinear, becomes bending. At the highest dose rates, the curve flattens out because of all of the available silver grains are developed and no more remain, regardless of how high the dose becomes. And this is called saturation. For dosimetry purposes, it is best to work on the linear portion of the curve. So you're looking at roughly here is anywhere between 0 to maybe 40, 50 dose. So this type of film requires a dose of roughly 50 centigrade to produce a net OD of about 1.0. So the graph used to provide a density to dose calibration is sometimes called an H&D curve. So for low doses, the relationship is, well, I just went through that. One must calibrate film for each radiation type and energy for each film type and for precursor conditions, which may vary over time. So, for example here, Kodak XV film is used to measure the dose in a plastic phantom at a depth at Dmax for a 10 MV film. The film was taken from the same lot as those used to construct figure 8.26. All films were processed at the same time, including a film that has not yet been exposed to any radiation. The unradiated film has an optical density of 0.22. The film with the unknown dose has an optical density of 1.4. What dose did the film receive? So the net is going to be the optical density minus the optical density of base plus fog. So it's this. If you go back and you look at figure 8.25, must have missed it. Either that or they skipped it. Yeah, let's see, what does it say? 1.4, roughly around here, I think. Oh, 1.18, sorry, my bad. So yeah, roughly around here, which is they're saying roughly about 50 gray. An advantage of film is that it has a high spatial resolution, which can be used to obtain a detailed map or picture of a dose distribution. It can be saved and read again later. Forms a permanent record. It's also widely commercially available and is relatively inexpensive. Disadvantages of silver halide film is that it has to be developed and it has a strong energy dependence for photons. It's not tissue equivalent and it's sensitive to light. A traditional silver halide film is much more sensitive to low energy photons than high energy photons. So the silver bromide emulsion has a high effective Z and is sensitive and high energy dependent. It's highly energy dependent, particularly below about 300 keV, where photoelectric interactions begin to become important because of its dependence on Z, cubic dependence on Z. So it can be 10 to 50 times more sensitive at low energies. So in the past 25 years, a new type of film called radiochromic has gained popularity as silver halide film has slowly disappeared. A trade name is gaffachromic or gaffchromic. This film has the advantage that it's not based on silver halide, but rather a radiation sensitive monomer. It's roughly equally sensitive to radiation energies. The unexposed film is colorless and it turns various shades of blue upon exposure to radiation. It is insensitive to ambient room light and is self-developing. No processing is required. There are a variety of different sensitivities available. EBT3 has a useful range of 0.2 to 10 gray. It can resolve features as small as 25 micrometers. It can be used for IMRT, VMAT, QA. For higher doses, EBT-XD or MD3V are recommended. Film RTQA is especially designed for machine QA. Film HDV2 is for high doses in the range of 10 gray to 1000 gray and is a very high spatial resolution on the order of 5 micrometers. It is recommended for stereotactic radiosurgery applications. Okay, so that's a good description of film. Diodes. Diodes are small solid-state devices that are used in electronics to convert alternating current to direct current. When these devices are irradiated, they produce a small current, even in the absence of an externally supplied bias voltage. Because they're solid detectors, they're very sensitive and they give a real-time readout. These properties make them useful for patient dosimetry. They are also used for depth dose scans and for beam profile measurements. They're not suitable for beam calibration, but they can be used as a daily check device to monitor LINAC beam output consistency. So let's go back and let's take a look at these pictures here. So this is a direct reading dedicated electrometer used for diode dose measurements. And you've got a drawing of a diode detector used for patient dosimetry. The diode is placed on the patient's skin and measures the dose at depth D max. So you place these on patient skin. They can be purchased with the appropriate buildup already on them for various energies. Diodes with buildup on them cannot be used to measure skin dose. For tissue equivalent material, the buildup thickness is several centimeters. For high energy X-ray beams, this would make the diode detector impractically large. Therefore, a high density non-tissue equivalent material is used, usually some type of metal. This can lead to anomalous behavior under certain circumstances. So the diode is attached to a cable to an electrometer, which measures the total charge flowing out of the diode. Diodes used for radiation therapy are unbiased. In other words, there's no voltage placed across them. The electrometer is usually dedicated, and its sensitivity is adjusted so that the dose can be read directly. The adjustment of the sensitivity is part of the calibration process. The diode is exposed to a known dose of radiation, then the electrometer is adjusted to read the known dose. Calibration must be performed periodically since the sensitivity drifts with time and with cumulative radiation exposure. The diode response varies with energy and to a small extent with field size. Diodes are rugged, reliable, and give an instant reading. Many clinics routinely monitor patient treatment with in vivo diode dosimetry. Diodes complement portal images. A portal image tells you where the radiation is going, but not how much is going there, whereas a diode can tell you that. Now, MOSFETs. MOSFET stands for metal oxide semiconductor field effect transistor. The MOSFET is a special type of transistor that is sensitive to radiation. A threshold voltage shift is measured, which is proportional to the radiation dose. Standard sensitivity MOSFETs have a calibration factor of about 1 millivolt per centigrade, whereas high sensitivity detectors have a calibration factor of 9. High sensitivity MOSFETs are well suited for measuring low doses, such as under a block or outside the radiation field. Diodes are not well suited for this. MOSFETs are small and lightweight. They're usually placed on a patient's skin. They provide an immediate dose reading and can be reused. The MOSFETs are connected to a reader, which in turn sends a signal to a computer. MOSFETs are read in terms of threshold voltage shift in millivolts. Computer software is used to require the readings, apply calibration factors, and store readings. One commercially available system allows up to 5 MOSFETs to be connected to the reader. In this case, one can gather dose measurements at 5 points. MOSFETs are sold without buildup. For measurements at Dmax, buildup must be placed over the MOSFET. The detectors have a limited life of about 20,000 millivolts. For standard sensitivity MOSFET, this corresponds to about 20,000 centigrade. And that's considerably shorter than the life of a diode. So the final thing in this section is the polymer gel. It's a tissue equivalent gelatin-based material that can fill containers in the form of spheres or other convenient shapes and used to assess the full 3D dose distribution of a phantom. This is a unique capability. Such phantoms can be used to validate radiosurgery dose distributions. Radiation causes polymer chains to form in the tissue equivalent gel. One frequently mentioned type of polymer gel is called bang gel. Magnetic resonance imaging can be used to measure the 3D dose distribution of the sample. Calibration data are obtained by irradiating test tubes filled with gel to known doses. Techniques have also been developed to measure the dose distribution using relatively inexpensive CT-like laser scanners. There are commercial firms that will ship a phantom containing a polymer gel to customers. Customer irradiating the phantom and then returns it to the commercial firm for dosimetric evaluation. So those are all of your solid state detectors.